Do you hear me? Test 1, 2, 3. Do you hear me? Great. There's a Moodle course. I've sent you in the Neptune message link. Were you able to register? Oh yes, quite a lot. And also for for chemistry, chemical engineer student. All right. That's a good start. So if you check your Neptune message, you will see a link. If you click on it, that's your Moodle course, your e-learning course. And I tried to set up to register yourself automatically. So if you click on it, you should be there. We will use it to share the lecture. Also, yes, why not? I should also share the YouTube link. Or I will upload later. Right now it's still streaming. So you will find here the lecture and the homework. Please try to finish your homework and not send me only the results, but also the steps you get it. All right. So I think you still remember what is angular displacement. Angular displacement is nothing else, just if you say a body moves on a circle, the origin is a straight line. So here is the theta equals 0, and here the angle increases. Means you can say, for example, the theta t depends on t like this. So this is the coordinate system. Of course, coordinate system we need units. In this case, I've chosen the units as p over 2, so it's p over 2, 2 times p over 2, 3 times p over 2, and 4 times p over 2 is a full circle. The only thing that can help us to calculate where is the body on the circle is divide the result. For example, this is 17 pi over 2. It's not easy to imagine where it is. So try to divide into n times 2 pi. This circle here is 2 pi plus the residual. And you can tell me after how many full circle where the body at, for example, t equal 1 second. So theta t is nothing else, just a funny, strange xt, the displacement vector. So it's the angular displacement vector. If we derive it, we will get the angular velocity. And if we derive the angular velocity, we will get the angular acceleration. Two things you have to memorize. This is the period time. How long does it take to move from one position back to the same position? And the frequency is 1 over period time. It can tell you how many times in a second the body takes a full rotation. Alright, one thing you can't forget even the velocity, so even the speed is a constant, the velocity can change. For example, when you move on a circle, and if it's a constant angular velocity, if it's a constant velocity, if it's a constant direction and then the same 1 meter per second in that direction, but if we calculate the delta v, that's a non-zero vector. If this is a non-zero vector, we can calculate the delta v over delta t, means it's not zero, the acceleration. And for example, for a uniform circular motion, when the speed is v, this acceleration is v squared over r. So let's say for a v equal 1 meter per second, if you rotate, if this body moves in a circle with the radius 1 meter, is 1 squared divided by 1. That means there is a 1 meter per second square acceleration every time to keep the body on a circular path. If there is acceleration, there must be force. The force is nothing else, just the m times acceleration. So if the centripetal acceleration is v squared over r, the centripetal force is mv squared over r. You can imagine if you rotate the ball with a string, and if you rotate faster and faster, this centripetal force must be larger and larger. At one point, the string can break when we reach the maximum load of the string. Oops. All right, we will come back to the circular motion. Just say something about the work energy potential. So the work is nothing else, just an energy transfer. We can calculate it by path integral of the force. Just some phrases. So the work done by gravitation on u means if it's a positive, the gravitational force will increase your energy. Work is energy transfer. Work can be also negative. If it's a positive, that means the work done by gravitation on a box. If it's a positive, means the box kinetic energy will be increased by this work. If the work is negative, like in the B, when, for example, there is a moving box, there is a displacement from left to the right, and if the force is opposite, this force tries to stop the body or tries to slow it down. That means the kinetic energy will be smaller. This is also an energy transfer or negative energy transfer. If the energy transfer is negative, the final energy of the system will be smaller than the initial energy of the system. And also, even with a non-zero force and non-zero displacement, the work can be zero, since the force is for constant f and the constants delta x or displacement vector. If they are perpendicular, the force is negative, because the first force is technically the scalar product of the force and the displacement, and at 90 degrees this is zero. All right, so if the force is not a constant over the displacement, we should, unfortunately, we have to integrate it. So in this case, the work is nothing else, just the path integral of the force. It's not too easy to calculate, but there are programs you can use it. So this 3D path integral is something what you won't learn how to solve it by analytical methods. You will only You can also use codes. Let's go to the, all right, just a minute. For example, what is the force done by this spring on this box by moving from here to here? We should create how the F depends on X. So this is the force, how it depends on the displacement from the zero level. The zero level is the relaxed position of the spring. So this is minus dx, and if we calculate this integral, that will be a positive value. So if we integrate from here to here, that's a positive value. That means the work done by the spring on this body from here to here is a positive, and as we expected, the kinetic energy of the box will be larger in the final state than it was in the initial state. Oops. Just some play with the math. The work can be expressed the path integral of the force, but instead of force, we can write F equal Fx, we can write m times ax, and if we play with the math, you don't have to understand all of the steps. By the end, we can have that work is something that changes this formula, and this formula we all know this is the kinetic energy. Sometimes we use the capital key for kinetic energy. So the kinetic energy is not an observation. You can derive it from the definition of the work and the Newton famous F equal m times a. So the work is something that can change this formula, and this is the kinetic energy. Let's see in what system it's true that the work only changes the kinetic energy. Let's say not here, all right, here. So only if we do not change the height of the body, because anytime we move the height of the body in a gravitational field, we have to calculate with the potential, and right now we don't want to calculate with the potential. And also it's true only if mu equals 0. In this case, the work, which is energy transfer, only changes the kinetic energy of the system, in this case of the box. All right, see the plot. There is a man tries to move a box, but you can see the force of the person and the friction is the same. So here we have to have work because there is a force and there is a displacement, and let's say this box moves with a constant speed. So the path integral of the force is something which is non-zero, but we can't increase the kinetic energy because the V remains the same. Where is the energy transfer? In this case, energy transfer is simple changes the internal energy. Technically, this is the temperature or heat of the body. So if we can't increase the kinetic energy, the work still is energy transfer, but we won't change the kinetic energy, but we change the internal energy. Another example, is when we, for example, you lift slowly with a constant speed a book. Take a book and speed from the level of table to level of table plus 1 meter. During the motion, when the box moves with the same speed, we do some work, which is plus work, since our force will go upwards and the displacement will also point upwards, but we do not change the kinetic energy, we only change the potential energy. So kinetic energy is something which depends on the mass and the speed of the body, the internal energy depends on the temperature of the body, and the potential energy depends on the position of the body in their system. So this is why we can say this is related to the configuration. So it's a configuration dependent energy. All right, let's do the thing by formulas. So if you lift a book from one position to the others, the work done by you on the book is the force times the difference of the two YB and YA level. If this is delta Y, and since we do not accelerate the body, therefore our force is m times g, the work done by me on the book is mg delta Y. And upside down, so if you release the ball and when it falls down, the force on the body is the weight, and when it moves from higher to a lower level, you can see the force is opposite to the displacement, and therefore if a book falls down, oh no, I was wrong. When it falls down, this delta R will go downward. So when the book falls down, the work has to be positive, because if the work is positive, the energy transfer is positive. That means the energy of the body has to be increased. And in this case, we know the book increases its speed or velocity. So what we can imagine for the potential is nothing else, just the energy storage, or one form of energy storage. So the higher the book, it saves more potential for changing its energy. So the potential is always the work stored in the position of the body in their system. Fortunately, the gravitational potential, so the work done by the potential energy, does not depend on the path we move the body from one point to the other. So from moving from A to E, it can be a normal straight line, not like that, or it can be anything. The work done by the gravitational force on this body during this path is always the same, because you see it depends only the distance from the zero level, and this is true for both kind of motion. Another conservation, energy has to be conserved. So if there is a closed system, means there is no external forces, no forces will change any energy. The sum of the energy has to be same. This is the mechanical energy. In this case, the form of the energy can be different. So down we have kinetic energy, here we have potential energy, and moving along this slope somewhere in the middle we can have both kinetic and potential energy. But technically the sum of these energy has to be conserved until it's a closed system. If there is an external forces, it of course can increase the sum of these potential and kinetic energy. This is true only for a frictionless example. But that's also true for a spring. If we push a spring and then release it, these systems, after removing our hand, this is a closed system, there is no external forces, only forces between spring and mass. And in this case, the energy stored in the spring and the kinetic energy of the box has to be conserved. And you can even imagine even more complex situation. Still, if it's a closed system and means there is no external forces and there is no friction, friction is the way how can we lose energy into the heat, which we can't get it back that easy. Alright, so if there is spring, changes in height, and changes in kinetic energy, the sum of all kinetic energy and potential energy has to be conserved. If we can talk about work, and this is something that happens in time, we can also derivate it. Derivating work, we can have the power. It has a historical reason why we talk about horsepower till now. You can Google it. That's all about James Watt. Alright, so we started with rotation, with circular motion, and then let's go back because we want to calculate the kinetic energy of the rotating system. And you will see it's not that easy. Few things, the omega, the angular velocity, also have a direction. And of course, if we derive a vector, the angular acceleration also has a direction. Let's fix few things. So if we rotate a body in the plane of your monitor or phone, if we rotate like this, come back to the previous example. So if we rotate like this, the angular velocity points to you. So from the screen to you. And if I want to know the normal velocity, so the velocity, not angular velocity, but the normal velocity of this P point, the velocity by definition is omega cross r, but since the omega is perpendicular to this plane and points to you, and this r is the position vector is inside the plane, these are perpendicular, we do not have to worry about this cross product, it's only r times omega. So the v is r times omega. We know there is a so-called centripetal force, centripetal acceleration, which is v over r, but if you replace the v with r omega, that will be omega square times r. This is true even for a constant rotation, a constant angular velocity. But if we also not only keep a body in a circular path, but also try to accelerate it, like having a positive angular acceleration, there is another acceleration, this tangential, that depends on the angular acceleration times r. So the acceleration that fills this P point is the sum of the centripetal acceleration plus this tangential acceleration. That's still something we can understand. In just a minute. Thanks for your patience. So let's go back for a rotating body. If we have an axis of the rotation, we can imagine that let's divide the body into small parts. That can be an infinitesimal small part of the system. Its volume is some delta V. Its mass is density times delta V. It is mi. It has a velocity. This velocity is nothing else, just the radius, the distance from the rotation axis times omega. Let's suppose the omega is a constant right now. So all the bodies along this blue dashed line has the same velocity, but at every other radius, the velocity will be different. So let's say I can calculate the kinetic energy of this small point, which is 1 over 2 mivi. Let's divide the vi into, and once again, this is a constant omega, constant angular velocity. Let's divide into Ri times omega and take the square of them. In this case, we can divide this formula, this original formula, into a 1 over 2, a part which contains the I, and something which does not depend on the position where I am, because we suppose this is a constant angular velocity. If we want to calculate the full rotational kinetic energy of the system, we can only sum of these points. So sum of all of the points in this body. That means go further. Instead of vi, we write again Ri and omega, and we will have a part like 1 over 2, and this is something which we can name as moments of inertia, and something which is true for the whole body. So the velocity, unfortunately, it depends on the position, it depends on the distance from the axis, from the axis of the rotation. But in this form, we can simplify the kinetic energy of the rotating system by 1 over 2 and something that depends on the body, on the mass and the shape, and something which is about how the body moves. So it's more or less the same like 1 over 2 mv square. 1 over 2 is something which is there. In the translational kinetic energy, m is something that depends on the body, and the v is something that describes how the body moves. Well, technically, it's not that easy to calculate the moments of inertia of any body, but for simple cases, we can do that. And simple cases, for example, for a ring, the moment of inertia is nothing else, just the mass times r square. In a piece of plate, this is 1 over 12 mass a square plus b square. For a cylinder, this is 1 over 2 mr square. So the solid sphere, so a full ball, it's 2 over 5. A basketball-like ball is a 2 over 3 mr2. So it always contains the mass, something that describes the geometry on the square, and in this 2 over 3, 2 over 5, 1 over 12, 1 over 2, here we describe technically the shape of the body. Let's calculate something. For example, at 0.2 meter r, the mass is 10 kilogram, omega is 10, 1 over s. We know the rotational kinetic energy is 1 over 2 omega square. This is the body, and the moments of inertia of the cylinder is 1 over 2 mr square. Let's just use the formula, and you can have that the rotational kinetic energy is 10 joule. And if you look at this calculation, you can see the kinetic energy of this rotating system does not depend on the L. But don't forget, this is only true if we rotate along this z-axis. So if you start to rotate, for example, along a horizontal axis, that will be different. Simple example, let's calculate it for a in this case a full bowl. Yes, I will correct it. This is not the cylinder, this is the solid sphere. This is 2 over 5 mr square. If you calculate it, this is 8 joule. Can you calculate the rotational kinetic energy of a thin spherical shell, so technically a basketball-like ball, if the radius is 0.2, the mass is 10 kg, and the omega is 10 1 over s. So please calculate it and write the result in the Discord. So now we calculated this one. Please calculate the basketball example. I can wait 2 minutes or 3. I forget to switch on the microphone. I talked a lot. Alright, so once again, can you double check yourself in the courses? Here we have Physics 1 and Physics for Engineers 1. It's for electric engineers, and the second is for chemistry, chemical engineers. Can you double check whether you see the course, because here you have the lecture and the homework and I have to use it. Any of you has any problem with that? Oh, that's great to hear. All right. Uh, this is for chemical engineers. So if you are so great that all of you can use it, why don't we have some other example like um, energy potential and I will find the example in a minute. One other thing, I can also add a book for you chemical engineers. I don't know whether I sent it or not. It's a pretty big. Can you double check whether you can download it from the Moodle? I hope yes. Just a minute, you can see it in a second. Wow, that takes time. I also can give this book for the electrical engineers. And let's find some example because wait, where is the circular motion energy transfer 181. That's a pretty long book. That's something you can know. The definition of power. And questions. Yes, so for example, wow, how can I move this one? Just a minute. So, for example, you can solve this example, this example, what is the number of pages? 211. So what if just a minute. From the book, please solve the page 211 example 25. That's enough. So try to be familiar with this book. Because right now it's much easier to learn something from the book than from YouTube videos, or it's up to you. Wait, don't find my presentation. So solve this example, send it, upload in the Moodle, and we will continue with the talk. Oops. Next time. That's all for now. Use the Moodle and let me know if you have any problem with that. I'm waiting a couple of minutes in the Discord for the questions, otherwise I stop the streaming.